Welcome my friends. Today we're gonna learn how to draw free body diagram on a graph paper. We're gonna draw free body diagram. Okay. What is the free body and why we use it? Free body diagram is the simple representation of forces acting on a mass or body. So we're gonna show our body with that for simplicity because for the Newton's law perspective, the shape of the object doesn't matter, right? If we neglect the air friction kind of things, right? So, in our case, there will be a mg downward force, and there is a tension 1 and tension 2. It's a simple case. Obviously, we'll have angles theta 1 and theta 2. So, and we'll learn what is the static equilibrium. Static equilibrium means our object is stationary, so there is no net force acting on it. So, summation of all forces will be equal to 0. So we know from the Newton F equals to ma. So if there is no F, there will be no acceleration and there is no motion. So in the static equilibrium, we're gonna check static equilibrium on the x-axis. So there will be no net force on x and y-axis is separately. In order to do that, we need to find the components t1x, t1y, t2y, and t2x. So let's write down what are the components in here. So t1y will be the t1 magnitude times sine theta 1. t1x will be the t1 magnitude times cosine theta 1. t2x will be t2 magnitude times cosine theta 2, and t2y will be t2 magnitude times sine theta 2 respectively. Okay, let's write it down the magnitude of our forces. Okay, I take from x1 of our experimental data and the angles, and then I'm gonna calculate the components. After that, I'm gonna draw up on a graph paper. So mg is, let's say, 7.5 Newton, 7.5 Newton. T1 is 2.5 Newton. T2 is 7.3 Newton. Theta 1 is 15 degree. Theta 2, let's say 75 degree. So from there, T1x will be the T1 magnitude times cosine theta 1. I will not openly write it down all of them. Okay, I'm just showing one case. 2.5 times cosine 15, which will be 2.415 Newton. You may use your calculator. You may use calculator on the computer, on your cell phone. In the exams, you cannot. Obviously, you may not use your cell phones, but you can use any scientific calculator. There will be a video about that, how to use different cell phone calculators and scientific calculators. I'm gonna uploading them. So let's find the T1y quickly. 2.5 times sine 15, which is 0.647 Newton. We need T2x, which will be 7.3 times cosine 71 degree. If you do the calculation, it will be 2.376 Newton. Okay, they are approximate results, not the exact ones, but that will be more than enough for our drawing, for our case, and which is 7.3 times sine 71, 6.900 Newton. Okay, right now we know the components. We can draw the free body. Let's focus on the graph paper. I'm gonna zoom the graph paper. So when you're drawing on a graph paper, the first thing you have to do is deciding the scaling. If somebody sees your drawing, must be understand what is the scaling. So I choose one big square is 1 Newton in both axes, and I'm denoting on top of paper. You can use the right lower corner or another portion of your paper, doesn't matter. And I'm starting from the middle of the paper because I don't know how big it will be. So I put my dot representing my mass, and I'm gonna draw the downward force mg, which is 7.5 Newton. So 1, 2, 3, 4, 5, 6, 7 Newton. For the 7.5, I'm gonna zoom it a little bit to see it better. 7.1, 2, 3, 4, and the 5. That will be my mg. So I'm zooming out. And you may use rulers for drawing a straight line. So I'm gonna use the drawing tool in here. I'm very lucky using the OneNote, but on the paper you can use the ruler. It will be much easier to draw at a one time. Yes, that will be my vector. Okay, we draw a straight vector for the mg. So let's draw the t1. So I have to draw a vector with angle. How can I supposed to do in a OneNote, or how can you do with your hand on the paper? So instead of trying to adjust the angle manually, we're gonna use the components. So we know that the summation of the components will give us the vectoral summation of them, will give us the resultant vector. So I'm gonna draw the components in here. Okay, first. After that, I'm gonna add them with tip-to-tail method, and I'm gonna draw the straight line for the vector. So start with t1x is 2.417, right? So 1, 2. 2.1, 2, 3, 4 is a little bit passing. So I'm gonna use dashed lines because it's not a vector. In the previous we only show the vectors, not the components. So for the discrimination, I'm using dashed lines and a different color for the components. So I draw the t1x. So I'm gonna add the t1y tail to the tip of the t1x, right? And then we're gonna sum them up. It's 0.647. So 1, 2, 3, 4, 5, 6, and somewhere like this. So that will be the t1y. So again, grab a ruler, use the tip to tail method. So start the tail of the t1x and end at the t1y's tip. So yes. So I choose my vector. Yes, this is my t1 vector with the scaling. So let's use different color the components of t2x. So t2x is 2.376. So 1, 2, 2, 1, 2, 2, 2, 3 is very close to 2, 4 because it's 2, 3, 7, 6. So let's call it t2x. And at t1y on top of it, it's 6.9 kind of. So up to the here, 1, 2, 3, 4, 5, 6, and 9. I will end up here. So that will be the t2y. So again, I'm gonna use the tip to tail method to draw it. So I'm grabbing my vector tool, adding tip tail and moving the tail. You see, I draw the vector on a graph paper with scaling. This is the T2. So we get the R free body. You see the difference? In here, the magnitude and angles are randomly shown, but in here we made it much more professional. Now, here is the question. What is the error in here? Is it okay or not? There will be some difference error. We can find it out. How? Let's talk about the static equilibrium. Okay, let's check if it's obeying the rule of the static equilibrium or not. And after that, let's show the error on the graph paper. Static equilibrium says that there is no net force on the x-axis, right? So what are the forces on the x-axis? T1x is in the minus I direction plus T2x in the I direction must be equal to 0. For the y, it must be again 0. So in here, T1y in j direction plus T2y in j direction plus mg in the minus j direction must be equal to 0. Or in other words, we can say that the force pulling left must be equal to the force pulling right as magnitude, right? If somebody pulling left and if somebody pulling right, if they are equal, it will be an equilibrium, right? In this case, if somebody pulling up some vector equals to the pulling down, there will be a static equilibrium. So summation of these vectors will be the F up, right? Summation of those two like pulling up force, and this vector is F down vector, drawing down. So let's check it. So what is the T1x? 2.415 Newton in the minus direction plus T2x 2.376 Newton. So what is the result in here? Obviously it's not 0, right? So it's kind of 0.4, yeah, 0.439 Newton, I think. The error in the y-axis. So if we want to show it in terms of percent error, put the difference, divide the one of the vectors. Multiply it with 100 to show the percentage. So in our case, let's use a calculator. So 0.439 over 2.376 times 100, not dividing, multiplying. So we have 18.4% error on the x-axis, and let's find out the error on the y-axis. Let's write it down. What are the forces pulling up? This is 0.647 Newton plus T2y 6.900 Newton minus 7.5 Newton. So let's do the operation with our calculator. So our error will be the like this, right? Let me calculate the error. Yeah, I think this is positive. Yeah. It doesn't matter because we are using absolute value. There is no such a thing as a minus error, right? So in the y-axis we have a much less error, 0.65%. So for the generic rule, okay, how we find the error on the x-axis? So f left minus f right divided by one of the forces, f left or f right. Take the absolute value, multiply it with 100 to get the error. For the y-axis, f up minus f down divided by f down or f up. I will just use prefer the f down times 100, like in my case. So we can find out the error by using the generic error formula. So let's draw our error on the graph paper. How? The Newton's law says that if I add these vectors tip to tail, the result must be 0, right? So let's add the vectors tip to tail, draw it again. If it's 0, there is a static equilibrium. If it's not 0, it will be not 0 in our case. We're gonna show our error with a vector. So I'm putting my dot again. 2, 3, 4, 5, 6, 7, and 7.5. My mg vector. So 1, 2, 3, 4, 5, 6, 7, and 7.5. 1, 2, 3, 4, 5. Right? This is my mg vector. Let's draw it with vector 2. Yeah, this is our mg vector. Let's add t1 to tip of it. So, like previously, we did it. First, draw the t1 x component, which is 2.4. I think we are here. 2.1, 3, 4. Yeah, in here I can stop. So that will be the t1x. I'm using again dash line because this is not a vector, this is a component. And for the 0.6, this is t1y component again. Now I can draw my vector t1. Okay, I'm grabbing my vector tool again. You see, I add tip to tail by using the tail method. That will be the t1 vector. Let's add the t2 in here. First, I have to draw the t2x, which is in the positive I direction, 2.376. So I'm kind of 0, 4, 1, 2, 3, 4, 5. Yeah. 1, 2, 3, 4. Come up to the here, and I have to finish here somewhere. So that will be the t2x. Let's go up for t2y. I have to go 6.9. 0.8, 1.8, 2, 8, 3, 4, 5, So 1, 2, 3, 4, 5, 6, and I'm at the 6, 5.8, 6.8. I have to go 6.9 up to the here. So that will be the T2y. So again, I'm drawing my vector. This is my T2 vector. You see, difference is very small. Actually, my error in here is very small. Let's check back again the values, numbers. Okay, what is the error in here? 0.4 Newton, like a half a square and a half a square, right? It must be like that. If I want to show it, it's very hard to show, right? To showing the error in this case. Let's zoom it. You see, even with the computer I couldn't draw. It seems like 0.1 Newton. Okay, it's very small. Yeah, even I couldn't draw, but on the graph paper I can draw it. Using my pen. So that will be the T error vector, like this. So we draw the error in our experiment. We draw free body of our experimental result, and we learn how to calculate. Thanks for watching.